basically starting, no, we're starting about 15 minutes early. So y'all stop me 15 minutes early. I didn't intend for it to be 15. I wanted to be here at 10. But there's always something. All right. Oh, almost forgot to pick up your test. Which reminds me, I probably should say this. Oh, this is this test, too. I was going to say if this is the... Yeah, the Cal 3, I thought I already took the key down there, but I've got the key to this one here. So... But let me say this about, sort of about that. I was just going to say, you may not have heard, we're getting awfully close to the end of the first mini-term. This week ends the first mini-term, and next Monday starts the second mini-term, so that we're right at midterm. And Wednesday of next week, they're going to have a midterm progress report we're going to have to submit, which means it'd be nice to have some sort of score for everybody. So I got your test here. If you get me something in Cal 3. Have you already turned in something there? Okay, either the paper or the first test. Okay. So, by Wednesday of next week. Okay. And then the volleyball team is hosting Sneed State this evening at 6 o'clock over on the Birmingham West campus. Okay, the Scholarship Summit. Okay, it was today on the Birmingham campus. It will be tomorrow on this campus from 1 to 3. You know where the cafeteria is? Okay, just next to the cafeteria, right next to it, right adjacent to it, is the faculty staff dining room. That's where it's going. No faculty or staff ever eats in there, but that's what it's called. It's the faculty staff dining room. Okay, and if you want more information about what's going on there, it's here. And also the NASA's Community College Aerospace College Program. That deadline is next Wednesday, 1 week from today. Okay. All right, we've got this up. Any questions on anything we've done so far? All right. Last time we started looking at some solutions by substitutions. This is Chapter 2, First Order Differential Equations, 2.5 Solutions by Substitutions. We did the first for homogeneous or homogeneous equations when you're talking about those that are have the same degree in every term. And we talked about those and how you can solve those. Now we're going to do a different one. And here is the difference. This differential equation, let me get my pen set up. Okay? Derivative of y with respect to x, I almost wrote curly D's there, I'm glad I caught myself, plus p of x, y. What is this looking like so far? I don't know. Linear. Looking like a linear except for this, f of x times y to the n. If that had just been an f of x there, linear equation, we take the p, take an integral of it, whatever you get from that, you e it, remember, okay, and go through that kind of stuff. This, however, has a y in that last term, which now makes it not a linear equation anymore, okay? Where n is any real number. Notice it doesn't have to be a positive integer. It doesn't have to be an integer. Any real number. Positive, negative, fraction, decimal, rational, irrational. It doesn't matter. Just a real number. This is called Bernoulli's equation. I always put Bernoulli's equation. And I don't know which Bernoulli this is. I think we talked about that last time, didn't we, right at the end of the class? There was a family of brilliant Bernoullis. Swiss, I believe they were. Now, where n is any real number. If n happens to be 0, then you got a linear equation, right? Because if y to the 0 is 1. So that's just a linear equation. If n is equal to 1, then you have a separable equation. Because if it's 1, you can divide both sides by 1, combine your b, that's separable, okay? Or it's also linear too, okay? But anytime n is not 0 and not 1, it could be between 0 and 1, it could be negative, it could be anything other than 0 and 1, here's the substitution you use, okay? U is equal to y to the 1 minus n, okay? Now, that looks like a great choice, doesn't it? Because if you do u is equal to y to the 1 minus n, then, well, let's just see what happens. It reduces this equation to a linear equation. Because then, 1 minus n, and you deal with the n, you get back to y is equal to 1, which was exactly what you wanted. Okay? Now, I think you can remember this. I think I'm going to need all the room I can get, so let me erase this, but hang on to the thought, okay? And let's do example 2. X times dy dx plus y plus, it's equal to x squared, y squared. Okay? Now, you reckon it's separable? No way. Linear? No way. Exact? Can't tell, but I doubt it. Okay? Homogeneous? No way. Okay? So, nothing works so far, but, now, is this even in the standard form I just wrote down? That's why I hated to erase it, but I hope y'all got it. What's wrong with it? You got that x in the way. So let's first deal with that. What do we do? Divide every term by x. Is that okay? Okay, I just wiped out the square and made it an x. Okay. So let me rewrite it slightly. I'll rewrite it here. Dy dx, everywhere I want to put a plus, I put an equal sign. Where I want to put an equal, I put a plus. Okay, I don't know what's wrong with it. Okay. 1 over x, y is equal to x, y squared. Okay. Still not separable. Still not linear. Almost linear. It looks a lot closer, but not. But you do know what your p of x now is, don't you? 1 over x, okay? And you know what the f of x is, just x. But you've got that y squared, so this is what form? From the big family? Bernoulli's, okay, this is a Bernoulli equation. So what's our substitution? 1 minus n. Okay, that's going to be your substitution. Okay? Now, what's your n? Let's identify that. N is equal to 2. Okay? So 1 minus n is 1 minus 2 is minus 1. Okay? So that's going to be the substitution. Okay? But we really want it the other way, don't we? If u is equal to y to the minus 1, let's get what y is. So this is u is equal to 1 over y. So y is equal to 1 over u, which is u to the minus 1. What's that? My hearing is, oh, that's n is equal to 2. Okay. That's from this. You know, the original form was y to the n. So first figure out what n is, then do this. Now, let's do a couple of things. Okay? First, we got a dy dx here that we have to fiddle with. Well, dy dx should be equal to dy du times du dx. Okay? Would you agree? Okay, okay. What is dy du? If y is equal to u to the minus 1, dy du is equal to we're not integrating. Differentiating. Huh?
We say we're doing dy du.
Yeah. Negative 1 u to the negative 2. Got it. Or you could do negative 1 over u squared. Perfect. Okay? All right. So that's what dy dx is. So let's write that here. That's dy du. So we have negative u to the minus 2 du dx, right? Plus 1 over x. Probably should have written that as a 1 over u squared, like you said, but let's do it. The y is it's going to write it as 1 over u, okay, plus x times y, which is 1 over u squared. So that's over u squared. All right. I am going to go back and rewrite that u to the minus 2 as 1 over u squared. Just like you were trying to get me to do, but I was being stubborn. Okay. Now, what looks like a good next step? U squared, I like the idea. So that gives you minus du dx plus 1 over x u. That's an equal sign. How in the world do those keep coming out pluses? I don't know. Okay. Duh. Okay. Equal x. Okay. Except for one little thing, we have a linear equation. What's that little thing? Negative sign. So let's make that a plus, that's a minus, and the middle one a minus. You okay with that? All right. Now we have what? A linear equation, right? And where do we go from here then? P of x is equal to what? Okay, and then we're going to do integrate this dx, so we'll integrate that dx, and what do you get there? Okay, we never do a plus c with that one. And how could we clean that up just a little bit? Another way to write it, negative log x. Okay, rule of logarithm. Yeah.
It's natural log of x.
You got it. Okay. Why do we want to do that? What's the next thing we're going to do? Huh? Your favorite of my expressions. You eat it. Okay. Okay. And that's why you want it to be a pure log. So when you eat it, it becomes what? X is negative 1. Now that line doesn't make sense the way it's written, but you get the idea. If I put an E here, then it would be okay, and put an E here, and that would be okay. Because that's what we're doing, okay? So, that is our integrating factor, okay? So what we do with it, remember I started to go to that line up here, this line here, you get minus, no, you don't have a minus. You have x to the minus 1 du dx minus x to the minus 2, isn't it? U, right, is equal to negative 1. Ooh, that's not too bad, is it? All right, now we hope that this part right here is going to be a perfect derivative. If it is a perfect derivative, it should be the perfect derivative of u times x to the minus 1. Is it? Let's see if it is. Product all right? What would this be? X to the minus 1 times du dx minus x to the minus 2 times u. Yes, it is. Since that is a perfect derivative, we can if that's equal to minus 1, you can do your dx over here and wipe it out here, integrate this, and integrate that. And what do we have? The integral of a perfect derivative is just x to the minus 1 times u is equal to minus x. Right? Okay, so what is u equal to? Multiply both sides by x, and you get u is equal to negative x squared. And here would be a good place to throw in your c, right? Maybe. Let's think about that a minute, okay? Not get too far ahead. Actually, they did it down here. They put their plus c in here. That's really where we did the integration, wasn't it? Yeah. Sorry. So I shouldn't have done it. Should have done it one step sooner. Okay. Huh?
Same thing though, right?
Well, a little bit. Okay, so now what we got to do is multiply both sides by x, and that gives us u is equal to minus x squared plus cx. There it is a little bit different. Okay? Now, but what is your u? U is equal to 1 over y. So we write this as 1 over y is equal to minus x squared plus cx. Okay? Now, flipping things around some, that gives you y is equal to, I'm going to write it this way, cx minus x. 1 over cx minus x squared. Okay? They wrote minus x squared plus cx. You just flip both of them. Okay? I like it better leading off with the plus, but they put the minus. And there is your one parameter solution. Okay? So, let's go back and review just a moment here, if you don't mind. By the substitution thing, if you have a homogeneous thing, your substitution is either u is equal to y over x or v is equal to x over y. Then solve for whichever one you're trying to eliminate, and either y or x, and go from that. Your Bernoulli's equation, you first determine what your n is, okay? Get it in standard form, Bernoulli standard form. Figure out what the n is. That's the exponent of the y on the right-hand side, okay? And then do u is equal to y to the 1 minus n. So that's always going to come up. Maybe not. I think always a negative number. Well, maybe not. There could be others. And then that's your substitution is u is equal to that y to the whatever 1 minus n was. Okay. Now, note that we have not obtained the general solution of the original nonlinear differential equation in example 2, since y is equal to 0 is a singular solution for that equation. Here's your equation, and this thing will never equal 0, right? 1 over that cannot be 0. The only way that would be 0 if 1 was 0. 1's not 0, okay? So y is equal to 0, but y is equal to 0 here would give you a solution, right? So this gives you all your solutions except y is equal to 0. So that's the secret. So to get a general solution, we might need to do a little bit more, okay? But they don't tell us what to do. So all we have found is a solution or a family of solutions, but not the general solution. Sort of makes you feel bad to realize we have it, but it's okay for now. All right. The next topic here is reduction to separation of variables. So it's another substitution, but this is going to, well, I guess there is a reason they call it reduction, but we're trying to get to separation of variables. So here's your differential equation. dy dx is equal to some function of a linear combination, ax, that is f there, ax plus by plus c. Okay, that's what your derivative is. Now, it says this can always be reduced to an equation that is with separation of variables by means of this substitution. And this should be a pretty catchy substitution. Let u equal ax plus by plus c. That ought to work, shouldn't it? Okay. Now, we got a little bit to do here. We need to do, this will be by is equal to u minus ax minus c, wouldn't you say? Okay. And then divide by b. and that gives you what y is equal to. Okay? So with that in mind, let's do dy dx. And what would that be then? Let's see, am I doing this the right method? Now this is true only if b is not equal to 0. I should put that in there. B not equal to 0. Because if it's not equal to 0, you can't do what I just did. You can't divide by 0. Right. Okay. So I'm jumping ahead in the generic case. Let's go back and actually do example 3. I thought they were going to do the generic case. They always have, but they didn't in this case. So let's just do example 3. Here's dy dx is equal to minus 2x plus y squared. Okay. Now, it didn't say it had to be a linear function. I may have said that, but it just has to be some function of x, y, and constants, okay? Minus 7. And this is the initial value problem that y of 0 is equal to 0. Okay. Now, the u needs to be a function of the linear part. That's what, when I said it has to be a linear function, u has to be. This is not a linear function here. Dy dx isn't a linear function, but it's a function of a linear function. Does that kind of make sense? Some function of u, and that function of u has to be a linear function. So here your substitution, let u equal the linear part here, negative 2x plus y. Okay? Then your function of this u is going to be z squared minus 7. Okay? That's going to be the function that uses that linear substitution. All right. All right. Now, what you need to do next is du dx. And what would that be? Negative 2. Okay? That's one thing that you have to do. Wait, sorry. Not just that. Plus, because y is also a function of x. Right? This is the first part, but y is also a function of x. So that would be plus dy dx. You see that? If u is that linear part that's in there, okay,
You'd be taking the derivative.
you're taking the derivative of this u with respect to x. That would be this thing with derivative with respect to x, plus this thing with respect to x. You don't know what this is, so it's just dy dx. This we do know is minus 2. Now, this transforms, or just a real simple algebraic manipulation, gives you dy dx is equal to du dx plus 2, right? Just add 2 to both sides. Okay? So instead of dy dx, we write that down. Du dx plus 2 is equal to, this is u squared, remember that was your substitution here, u squared minus 7. Yay or nay? Okay? Now, let's go on and subtract 2 from both sides. All right with that? That gives you du dx is equal to u squared minus 9. What do you think we can do with that? Say again? Not quite. Separate the variables first. This would be d u over u squared minus 9 is equal to dx, right? U squared minus 9, you divide and multiply, write it in differential form. You got that. Now integrate. And what does that give you? Uh-oh. Uh-oh. Uh-uh.
Wait, what did you say? You said integrate, right?
I said integrate. If that was u minus 9, that would be a natural log. It's what?
It's a trig substitution.
You could do it by trig substitution or by partial fractions.
Yeah.
And that will give you a log, okay, when you do that, but not as is. So we have to go off to the side here somewhere and do we're integrating this du over u squared minus 9. Well, let's just forget the integral sign and forget the du now. Just 1 over u squared minus 9. And let's write that as 1 over u plus 3 times u minus 3. Factor, folks. Okay. Now, maybe I haven't asked y'all this question. And if it offends anybody, I won't do it. Okay? I won't do it anymore. But if I say, what's the F word? It's factor. Okay? In many ways, right? No, okay, we won't get
I
into
wouldn't be answering that question.
you were ready to answer it, weren't you? Okay? Yeah. Yeah, but that's what we do, is factor. Okay.
How can you look up the table of u squared minus 3 squared?
Yeah, you could, and use a trig substitution. Is that what you're getting at?
Yeah.
Perfectly fine. You can do that. I think this is a little easier, but maybe not. Okay? It should come out the same thing.
Yes.
Okay? So, what do you do with this?
You said a over
U plus 3, and then you do what? Yes, and you get 1 is equal to? Okay, and then you do something that's really a big trick. It doesn't...
Just say u to...
Huh?
Say u to either 3 or negative.
Okay, when you set u equal 3, what you get? 1 is equal to b times 6. So b is equal to 1/6. And then you could do the other one and say this is let u equal 3. Here, let u equal negative 3. And what do you get? 1 is equal to negative 6a. And b goes to 0. I mean, the u plus 3 goes to 0, so that's out. So that implies that a is equal to negative 1/6. So now we go back and put it in here. And this will be, if it's all right, I'm going to put the plus first. I just like pluses first. So I'm going to put 1/6 the integral of the positive is that 1 over u minus 3 du minus 1/6 the integral of 1 over u plus 3 du. That's ugly. Oh, there it is. Okay. And that's equal to an integral. Yeah. That's integrating this side. Integrating that side gives you x. Okay. Now, yeah, well, let's put our plus c down there. I was going to see if there was an easy way to get it, but I don't think there is. Okay? So this gives you 1/6 natural log of u minus 3. We'll put that in absolute value bars. minus 1/6 natural log of u plus 3, I'll also put that in absolute value bars, is equal to, I don't know if I want it to be C or log C, but we'll see. C. Okay. I would think so, but let's just see what happens if we make it log C. I don't know. Yeah, we're going to E everything on. Okay, yeah, we got some other things to do here. Let's multiply both sides by 6. Is that okay? And that would give us log of absolute value u minus 3 minus log of absolute value u plus 3 is equal to 6x. Let me just leave it plus c. We may make it log c later. 6 times c is still a constant. It's just some constant c, whatever it is. Okay? Now we can do something here. What is that? Yeah, so that's the log of u minus 3 over u plus 3 is equal to 6x plus c. Now let me see, just to avoid a lot of mess. Yeah, we're okay. This is fine. Okay? Now what we're going to do now is it. Okay. And what will that give us? U minus 3 over u plus 3 is equal to e to the 6x plus c. Which, by the way, is e to the 6x plus e times e to the c. But e to the c is just some constant, right? So that will be, let's take it off here and put the c there. Okay? Is that all right? Again, I'm being very sloppy with my c's. Okay? Now, at that point, we need to solve for u at some point, so let's get around to doing it. How are we doing on time? Oh, we're almost out. Let's just do it real quickly. U, all right, take care. Minus, let's see. Let's put in what u is. U is 2x minus 2x plus y. So minus 2x plus y minus 3 over minus 2x plus y plus 3, yeah, is equal to c e to the 6x. Okay? Now, oh, I'm sorry. I did it too soon. We should have solved for u first. That's what I was starting to do over there, but glanced at the page and botched it. Okay. Do we have time? Just barely. Let's do it here. Okay, forget this one. Sorry about that. It would work, but it's just a lot more work. Let's try to keep it as simple as possible. Okay. All right. U minus 3 is equal to c e to the 6x times u plus 3. Okay. I'm going to erase that at the top. We've already done it. We bought a t-shirt, so let's get rid of it. Okay. Probably could erase the next line too.
value.
Right.
I thought I didn't notice that was an absolute value. Looks like natural log minus 3.
Oh,
I was like,
making fun of my writing. I hear that. Okay, I'll remember that on the next test. Yeah.
okay.
Yeah. No, I'm just kidding.
I was like, man.
I'm just kidding. Yeah, it does look that bad, doesn't it? My U's and N's, yeah, they're terrible.
Well, on the test,
Yeah.
like number 7, where you gave us that awful second differential,
Yeah.
I had to do it like 3 times.
Yeah.
Did you get it?
Yes. God, at like 12 o'clock last night, I spent a couple hours doing it wrong.
Okay. Basically what you do is distribute this, okay, in that. Then get your U's together and move the plus 3 to the other side. We're out of time. And then divide out, factor out the U's, and then you divide by what's left. And believe it or not, you come out with something that looks like this. I'm sorry we don't have time to do it, but it's all quite doable. U is equal to 3 times 1 plus CE to the 6x. It's just amazing. They come out this similar looking over 1 minus CE to the 3x. Because you see the things are all there. This is U e to the CU e to the 6x and 3, and then when you factor out the U, then they all look a lot like each other. Now, at this point, we go back here and plug in minus 2x plus y. So this will be minus 2x plus y is equal to this thing. Okay? And then you add 2x to both sides. And you get y is equal to 2x plus that thing. And there's your final answer. Oops. I've got my plus and minus in the wrong places. I thought I was copying them right. I thought I did, but then at the bottom, they have them backwards. Oh, wait. They went back and plugged in our thing. Yeah, they eliminate the C, and you wind up with C equal minus 1. And that's what changes them around. So, sorry about that. I forgot we still have to evaluate that. But, we've run out of time. Homework exercises here would be any of the odds 1 through 9 that are in the back of the book. 11 or 13 if they're in the back of the book. Any of the odds 15 to 19 if they're in the back of the book. 21 if it's in the back. Any of the odds 23 to 27 if they're in the back. And 29 if it's in the back. And then if you find any of the discussion questions in the back, you can look at those too. There's a good Italian pasta question, number 35, Riccati's, no, that's a different thing, but equation. You could write on who in the world is Riccati, or, how did he come up with this equation, or what difference does it make, that kind of stuff. Later you'll see a logistic equation listed. I think I mentioned that when we're doing 1.3 or something way back, we had that. Now, the only thing left in Chapter 2 is numerical methods, and we're going to do that. It's called Euler's method. It's not the most efficient numerical method, but it's a fairly straightforward early one to do, and then we will, I'll give you your second test. So it'll probably be sometime next week. I'll get the second test to you. All right. And y'all can work together on the test as long as learning's going on, So I don't mind that y'all compare notes. Because I know you guys, and you're not going to just copy someone else's answers. You're going to figure out what is going on.
Huh? Well, I guess you could
But what good, that doesn't do you any good.
Yeah.
But if you can find out where you made your error, you've learned something, okay? I'd rather you find out where you made your error than me find out where you made your error. It's a lot easier for me, okay, so.
Well, I did 7 and 8 last night, and it was about like 1 o'clock. I started over 9, and I was like, God, I
Go to
have
bed.
no idea what I'm doing anymore.
Yeah.
I was like, I solved it. I was like, okay, that equals that. I'm like, I got 9.
Yeah, that's the thing is.
One that's giving me help.
Yeah, the thing is, probably number 9 is as easy as you thought it was. I mean, they don't follow difficulty. Yeah,
You're too much in.
yeah.
Yeah. Number 7, it had basically like 10.
Oh, I know, it's awful. It was in their material, and I thought it was going to be something that came out pretty neatly. I thought, oh, this will be fun. Oh, no. Because I had to work the thing, too. I thought, oh, I hate this. Yeah.
Once I figured it out, though, it was very, like, empowering, I guess.
Yeah.
You tell me what the secret is. I'm still.
Yeah.
Man,